Hello, everyone. So I think we have enough people to start the lecture. Last 2 weeks, we spoke about like some machine learning concepts in general. We spoke about neural networks. We spoke about convolutional neural networks, and we did two sets of labs. One was about just basic data science, just to make sure that everybody has the requirements or Python knowledge needed for this course. And then after that, we did a lab where we spoke about how to build a model or a neural network for convolutional neural network in PyTorch. And of course, how to use transfer learning for building such neural networks. If I'm not mistaken, we didn't finish the part where we need to speak about, let me see which part did we finish. I think we stopped right before we started speaking about transfer learning, right? And we didn't do the TensorFlow part. Okay, nice. So let's finish the lab really quickly and continue the new lectures. And the new lecture will be on generative adversarial neural networks. We're sharing screen. Very well. Can everybody see my screen so far? Anybody here?
Yep, everything good.
Nice, good. So very well. As we said, we have seen different parts in the last lab. So first we spoke about what is ImageNet in general. And then we saw some of the winners of this ImageNet challenge. And from there, we saw how can we access or how can we directly use these different models and their pre-trained weights from PyTorch using the Torch Vision Models module. And we basically just went through the different layers that exist in a typical neural network. And then we spoke about transfer learning in general and fine-tuning specifically, and how it's pretty useful to basically use a pre-trained model and not start from scratch. We saw that in order to train basically a neural network in PyTorch, what you need is 3 parts. The first part is the data set. The second part is the model itself. And the third part is the training algorithm. In the first part of the data, you need 3 main parts again. So the first one is the transforms, the second one is the data source, and the last part is the data loaders, right? So this is the combination that you need. And of course, you need to do it both for training data and for testing data. Now for the module itself, or the neural network, usually it's composed of 2 sections. The first section is the init section. And this is where you declare all of your different layers. And there's the forward section. This is where you declare the logic or the sequence of the layers that you're using. And since we are using just sequential models, then this logic should be pretty simple, right? So it's just calling different functions after each other, right? From here, pretty simple. Now for the last part, which is the training algorithm, as we said, all of this code is just for beautifying and doing a lot of visualizations and giving you all of these values and stuff. But this is not what really matters. All of this is just basic, what is it called? Python programming, right? To get all of these values for the accuracy per class and stuff like that. So this is all something that is related to well, basic machine learning and basic Python programming. What's really important for us is the following, right? So we have the criterion, which is the loss function, cross entropy loss in this part. I'm assuming that everybody already knows what cross entropy loss is, unless Randall has still didn't take the decision trees part. Is he around? I don't think he's here. Randall. Okay, he's not here. So this lecture is going to be pretty smooth. So the rest of you guys should already know what cross entropy loss is. And so yeah, this is the criterion. The optimizer is the algorithm that is going to basically do the training of our neural network, and it's going to find us the best parameters in for our task. How we do that is we usually specify a different optimizer for every specific part of the neural network. This allows us more control over the neural network. So for example, here we are creating a stochastic gradient descent optimizer on the parameters or on the learning or on the values of the weights and biases of our neural network. And of course, if we had multiple neural networks, we will be replicating this line multiple times for each one of them. The main part is basically to go and iterate through the training loader, and from there send the data to the GPU, send the data through the model, which should already be in the GPU, and then calculate the loss, back propagate that loss, and then make a step in the gradient's direction. Of course, it's always very nice to basically calculate or make the gradients that are saved by default by PyTorch in the optimizer, set them all to 0 in order to make sure that there's nothing outside of this part that it is actually influencing your learning. All of the rest is just basic, as I said, basic Python programming, and you should already understand what is happening here. So here we can see that the model, after just one epoch of course is not enough, but after one epoch, it was only able to get 50% accuracy. Now, just a small question, right? Given that we have 10 classes, and let's assume that they're all kind of balanced, is 50% accuracy better than the random classifier? Basically, is it good, right?
No, it is not.
It is not better than the random classifier, because random really is just either correct or wrong, right? So it's like 50% chance. Is that correct?
Yes, it is. Exactly.
Anybody else has any different opinions about this?
I think that it's like the same.
Yeah, they're kind of like the same as a random classifier, right? Is that what you're saying, Lara? Anybody else?
Yes, that's it.
Okay, so basically, there are like 3 options. Either this is better than this one, either this one is better than this one, or this one, or basically they're kind of overall the same. Can somebody else give me maybe a different point of view?
I think it will be incorrect because we have 10 classes, so random classifier will give you much smaller percent of accuracy than 50. Like
Can you tell us what would be the value in that case?
10%? Yep.
Yes, 1 divided by 10. Very well. That's correct. So as your friend Sergey has just said, the random classifier in this case does not give you 50% accuracy. It gives you 10% accuracy. Meaning our model in here is actually multiple times better than the random classifier, because it's not just either true or wrong, right? There are many other options, which are class number 1, class number 2, class number 3, class number 4, class number 5, class 6, 7, 8, 9, 10. So usually the random classifier, if we have like a very balanced data set and it's a very beautiful random classifier, it should give you something around 10% accuracy. So here in this case, true, 50% is a huge improvement over the random classifier, but still it's not that good, right? So it's still not where we want it to be. Sorry. Now that we have this model that we have created from scratch, right? Remember, this model, we created every single layer from it from scratch. Now let's go to a model that uses that leverages basically a a pre-trained model, right? So again, as before, we normalize the data. We, what is it called? We build the data set source. We build the data loader. This is the batch size. This is the number of workers. Everything is here made. But now for the neural network, you will see that it's much smaller, right? So what we have here is we will take our neural network, ResNet 18. Here it is, pre-trained. And then we will set it all to trainable equals to false. Now I will just give you like a small resume of what you generally would do in this situation, depending on whether you have enough data or not. So in the case where you have a lot of data, and here, not enough data. Nice. And here you have, how do we say, similar classes. And different classes. So in the most optimistic situation is you have a lot of data and you have similar classes. In this case, basically you take this pre-trained model and try to basically retrain it, but focus on the last layers, right? So one person would try to basically do 100 iterations where he is basically training the whole model, but then he would freeze the first few layers, like at the end, freeze the first few layers and only retrain or continue training basically the last layers, right? Now, if you have a lot of data and you have completely different classes between the source or the, what is it called, ImageNet, and between the classes that you are working with, let's say, for example, heart disease, between these heart diseases. So in these cases, you would try to opt and retrain the whole neural network, all. But when you don't have enough data, you cannot afford to retrain the whole neural network. So in these cases, what you should do is freeze the initial part. So freeze the first layers and retrain the last. Same thing happens here. Okay. So this is just like a small recap of what you should typically do when you are training a new neural network based on something that was already trained before, right? Yep. Let me just check. Maybe somebody wants to join or something. Okay, so this is no course. No, yes. So yeah. So this is why we set this trainable parameter to false. If, for example, we wanted, let's go back to this ResNet 18, right? Here is ResNet 18. If, let's say, for example, I wanted to, what is it called? Freeze this layer exactly. So what I do is simple self.network.conv1.trainable equals to false. Now let's say I don't want this one, I want this one, right? So this is a bit more hidden. So this one would be self.layers. We can see that layers is a, what is it called? An array dot layers. Let's say I want the second, okay, so it's called layer one, so not layers. Layer one, and then at one, and then dot, let's say conv1 or something like that, or conv2. Let's go for conv2. And then we set trainable equals to false. And this is how the neural network or the algorithm will know which layers to freeze and which layers not to freeze. Now, Usually you don't do it layer by layer, but you could do it combination by combination. So for example, you might want to freeze layer 1 completely. And in that case, all you need to do is, again, self.net.layer1.trainable equals to false, right? No need to freeze every single layer. Basically, if you freeze the parent, all of its children are going to be frozen. So this is how the trainable is operating. Basically, if I wanted to freeze just this layer, it's going to freeze on its own. But if I want to freeze, basically, let me close this. Yeah, if I wanted to freeze layer 1 completely, just freezing this layer 1 would freeze convolutional 1, would freeze convolutional 2, and this one and this one. So it would freeze us all the 4. And if I want to freeze the whole neural network, all I need to say is network.trainable equals false. Pretty easy. Let's come back. So here we are setting the network trainable equals to false. This will freeze the whole neural network. And if we go back, sorry, last time going back. So here we will see that the last layer is called FC, you see? So this last layer is the one responsible for making the classification. And since it has 1,000 classes, we cannot use this last layer. What we need is a layer that kind of ends with the same number of classes as what we have, which is 10. So we replace it with exactly the same type of layers, NN layer, and we have 512 as input and 10 classes for the output. The rest is exactly the same, right? So train and evaluate. Now let's see, in one epoch, as we can see, the model now, instead of giving us 50%, it gives us 85%, right? So we can see that in the same time of training, this model gave much better results than the model that we created or we trained from scratch. Very well. Now let's speak about TensorFlow. Does anybody want to basically speak about TensorFlow? Or before we go there, does anybody have any questions about PyTorch? I see Randall has joined. Welcome.
I have a small question.
Yeah, go ahead.
Can you return back to the normalized line? I have a question why we're normalized around 0.5.
That's a very, very good question. Usually you would not need to normalize around, sorry, let me just close these. Airplane mode. Hello, are you guys, can you guys hear me again?
Yes.
Yeah, sorry, I was having too many notifications from another course I'm teaching, and the students are asking a lot of questions. So I just turned off the thingy. Nice. So you said, why are we normalizing by 0.5? So here, but just so you understand, this is the mean for channel. So we have RGB, right? Red, green, blue, well, RGB. And here we have 0.5 for the mean, 0.5 standard deviation for the red channel, 0.5 for the mean of green, 0.5 for the mean for the standard deviation of green, 0.5 for the blue, and 0.5 for its standard deviation. So they're all coming from this distribution. Now, why exactly 0.5, 0.5? Usually what you should do is just go to the model that you are working with. For example, we're working with ResNet 18. What you should do, just go to the paper, to their original paper, and find the values that they used for the normalization and use exactly the same values, right? So for some, let's Google it right now together. Normalization for VGG 18. Nah, there we go. So you see, different values. So this is the normalization for VGG 18 model. Now let's go, for example, for give me something from what we have seen here. Inception V3. Okay. Inception V3. Yeah, there we go. So usually for every single model, you have a certain set of what are they called? Normalization values that work well for that model. So these are the values that the authors have used to train their model. And since you're using a pre-trained model, it's best to keep the same values that they have used. Now, if you're going with something from scratch or like something you're building your own, so in that case, you can do whatever you want, right? You could put it, for example, around 0, 0, 0 with 1 in normal standard deviation, or you could put it in 0.5, 0.5, as you wish, right? So apparently the thing that I just did for blocking these notifications did not work. Let's see, manage notifications. Yeah, hopefully now there will not be anything. Yeah, let's continue. Did that answer your question?
Yes. So it will be
Yes.
our hyperparameter.
Yes, technically it's a hyperparameter that you need to fine tune, but in most cases you would want to go with the same values that the original authors of the network you're working with have used. Yes.
Okay, got it. Thank you.
Thank you. Great question. Anybody else has any questions about PyTorch so far? Some remarks, maybe how easy it is, how predictable it was, or how unpredictable it was. For example, for Randall, how is it going with the machine learning course? Are you advancing so far? Did you start speaking about decision trees and stuff like that, or not yet?
Nowhere near that. We just finished like logistic and linear regression, gradient descent and all.
Oh, really?
Yeah.
Hasn't it been like 5 lectures or 6?
No, just 3 is now.
Ah, you study like 1 lecture per yeah,
per week.
Okay, so,
lecture per week. Yeah.
Not like the bachelors. I thought they changed everything. Okay.
Okay.
Nice. Good. Nice to know. Nice to know. So now for the TensorFlow way, simple. Again, you are importing the layers and importing the necessary libraries. Here now you are loading the data set. Again, very simple. But in this case, the data set you're using is not coming from a loader. So there's no like loader who's loading it dynamically. Now you're just getting the data as it is. So here in test images and train images, you're getting access to what is it called? To a NumPy array that contains basically the images themselves directly. So here, for example, just some pre-processing. Yep, and just we're showing the values. Now, how do we build the model? This is one way of building the model. This is kind of the old way that TensorFlow was being trained with. And this way is built, basically you define the type of the model. Somebody has a question. So what is exactly a loader? Very good question. What is a loader? Let's do it like this. I'm sure you guys already have seen a define function. Let's say maximum for I in range of maximum yield I. And here we're going to be doing for I in function, sorry, not function, for I in, yeah, function, this is the name of the function, sorry, maximum. You're going to do something. So basically what's happening is you are yielding or you are creating these values as you are walking in this for loop, okay? So you're not really returning a range. You're not returning directly an array in this function call. Every time you enter the for statement, you are calling or you are continuing the execution of this function. So this is what the difference between having the data as they are directly and having some sort of a loader, right? So the loader allows you to load the data when you need it, right? So basically the data is still in the store or in the hard drive, and every time you are going through the for loop, right, for data in train loader, you are loading the new data to the RAM. But in this case, the data itself is already in the RAM and you're using it all on its own. You see the difference?
Yeah, yeah.
Very well, nice. So here we are speaking about the Keras model. So Keras basically simplified it. Previously, before Keras, TensorFlow was disgusting to look at. Basically, you see all of this code just to build a tiny model. For TensorFlow, it was, let's say, 20 lines more than this, just to build like something very basic. It was disgusting. But now it's getting a little bit better. For now, what they are saying is, you need to specify what type of model you're working with. As we have said previously, so far, all the models we're going to be working with in computer vision are sequential model. So there are sequential models in which you have like layer 1, and then you send the data to layer 2, and then you send it to layer 3, and then you send it to layer 4, and then you get the output. So this is what a sequential model looks like. There are other models which have like layer 1, layer 2, layer 1 sends to layer 2, and then layer 2 goes back to layer 1 for like 5 times, right? So the data continues to come, that you continue looping here like 5 or 6 times, and then you go to the output layer. So this is like the difference between the models. And the models that we are working with for computer vision, mostly the model that I just showed you works with text, right? Because text is not just like one value that comes to you as an image. Text is something that has different sizes and stuff. So you need something more flexible. But for images, we don't really need to worry about that. They're all like the same size because we resized them. So here we are specifying that now we are going to build a sequential model. And now we're going to build basically the model layer by layer. And if you see here, unlike PyTorch, in PyTorch, we had one block where we define the layers, and then a second block where we define the order or we define the logic, right? But for TensorFlow, you define the layer and the logic in the same place, right? So this means here you are more of a dynamic situation, and here this is like a static situation, right? And this is why this is called dynamic graph for PyTorch, and then static graph. Here, the graph that you are building, the graph basically the neural network, is very static and does not change depending on the data or depending on the different situations. Very well. So here, again, very simple stuff, convolutional 2D, the kernel size, the activation, and then we specify the input shape for the first one, but then the others, we don't need to specify it for them. Convolutional 2D, again, the number of filters, the size of the kernel, then the activation, back spooling, dropout, flattening. The flattening is just, flattening is simple. So basically we take an image like this, and then we make it into a 1D vector, very simple. Now for dropout. Who doesn't know what dropout is?
I'm not sure actually, but I think it's when you do gradient descent, after you reach that some sort of minimum, you decide after some point, after some iteration, you drop out. Is that correct?
Not really. That's early stopping, I think you're describing. But
okay.
Dropout is basically very simple, right? Now you have here, first layer, sending values to second layer. In return, it sends values to the third layer. Remember, every single, so for example, like this. Yes. So basically this one, 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 all of them are sending their activations to this neuron. Dropout is very simple. Dropout tells you randomly some of these activations will not pass through for some reason, right? So we will not let some of these activations go through, right? What does this thing give you? First thing, it will force these activations or these neurons to basically start learning better or start finding information through different roads or routes, right? This is first thing. The second thing is it will allow you to do kind of a search in different, what are they called? Hyperparameters of the neural network. So instead of having a fixed neural network of, let's say, 10 layers here, 20 layers here, and 30 layers here, or 30 neurons here, 20 neurons here, and 10 neurons here, now you are kind of searching between 8 neurons from 8 till, let's say, from 16, let's say, till 20, and then from 21 neurons till 30. Basically, during your training, you are experimenting with different sizes or different number of neurons per layer. And this is quite random, right? So you are kind of searching throughout this big space of hyper parameters or of these different, let's call it hyperparameters of the neural network, right? So this kind of allows you to do better or build a more resilient neural network. Okay? Does that kind of simplify the concept for you a little bit?
Yeah, that helps. Thank you.
Very well. So I'm sure the others, you're already familiar with what dropout is, but this was just like a small introduction to random. After that, we finish with an activation of softmax. Now, for those of you who already know the difference between softmax and what is it called? Sigmoid and all of these things. So can somebody tell me what's the difference between softmax and sigmoid?
We use sigmoid when
I can't hear you very well. I think it's like you're very far from the mic.
Can you hear me now?
Kind of.
Is it better?
Yes, now it's much better. Yeah, now it's much better.
Okay. From what I understand, we use sigmoid activation function when we are dealing with a binary classification task.
A binary.
Yeah.
Nice.
While we use softmax when we have more than 2 things to classify.
Very well. Nice. That's very good. So basically, softmax is kind of the extension of what is it called? The other girl. This girl. What is the name of this function? Forgot the name.
Sigmoid.
Sigmoid. Thank you. Yeah. So softmax is kind of the extension of sigmoid, and basically what it does is simple. Now let's say the neural network, it has 10 outputs, right? So the first output, let's say it's 5. The second neuron outputted 120. The others outputted 0, 5, 2, 3, 0, and 12. Now, how do we treat this as a probability, right? So as we said, we want the output of our model to be something we can interpret as a probability. If it was just one value, we could do softmax. We could do sigmoid, right? If it was just one value, sigmoid would give you like probability 80%. That means it's okay. 20%, that means it's world class. But now we have 10 classes, right? So we kind of need a probability, and we also need that the values or the sum of these probabilities gives you 1, right? So this is what softmax does, right? So softmax allows you to convert these values similarly to this, and then it makes the sum of all of these things equal to 1, and giving you like the output of the whole neural network equal to like a probability distribution. I'm gonna send you a very simple or like a quick link. Here we go. Let me open it up for you guys. There it is. This is just simply a small how-to that I wrote when I was working like freelance thousands of years ago. But basically just will explain to you what's the difference between binary classification, mutually exclusive multi-class classification, and non-mutually exclusive multi-class classification. And for each case, what loss should you use and what activation function should you use, right? So in this case, for example, when they're non-mutually exclusive, that means you could have, what is it called? Sigmoid plus a loss function that works for multi-classification. But if they are mutually exclusive, in that case, then you should use softmax, right? Instead of sigmoid. But it's pretty simple. You could check it out. You will find like the differences between each one of them. And it's quite useful if you're going to use TensorFlow especially. But if you're going for PyTorch, you really don't need to worry about these things. And here you just compile basically the model that you just created, giving it the name of the optimizer and the loss function that you're going to use. So sparse categorical cross entropy. There is categorical cross entropy and binary cross entropy. The difference between sparse and non-sparse is just basically one uses the labels as one hot encoded labels, and the other one uses labels as 7, 8, 9, 10. And the metrics for evaluation will be accuracy. You train the model. So this is model.train.fit. You give it the training data, the number of epochs, and here you get the history. The history is simply this, right? So basically it gives you the accuracy and the loss at each step of the training in like some sort of a dictionary report. And here is the evaluation. And as you can see, our model gets almost 99.1% accuracy, which is very good, right? But it's a very simple data set, just MNIST. Now, after TensorFlow 2.0, which was like recently published, but recently that's when I was pretty old, so I'm getting old. Sorry. When was it published? I think it was published like a couple of years ago. Yeah, 2019, right? So it's still quite recent. And in here, now we're going to start working a little bit like, sorry. Was the quiz already conducted? No, we did not have a quiz today because we didn't really cover much in the last few weeks, in the last 2 lectures. It was like very basics. So hopefully next week we will have our first quiz where we will kind of speak a little bit about what are they called? Adversarial neural networks and segmentation and stuff like that, right? But for now, there is no quiz. It's pretty easy what we're doing. So here we're kind of going back to the same topic of like having a data set, creating a data set, and then creating this kind of data loader on top of it, right? By using this .batch.shuffle stuff. And then we have this the same manner of creating models by separating the layers from the logic. So remember, here the model was being created all at the same time. Here again, it is being separated, just like PyTorch. So that's a good improvement. And for the rest, again, we have a very similar stuff. We go through the data and we train the model. Now, instead of having, what is it called? The optimizer keeping track of the previous gradients, we have this something called as the gradient tape. The gradient tape is keeping track of the different gradients that are calculated at different steps of the training. And especially for things like recurrent neural networks, we kind of need this history to do the training. But for computer vision tasks, we don't really need the tape to kind of focus on it a lot. This @tf function is just to speed up the calculations, right? So this just kind of converts this function into something that is heavy on the GPU and makes the processing a bit faster for the training. It really doesn't do anything fascinating. And there we go. Here's the training again. Very simple, very basic. And that's it for TensorFlow and its differences, or the differences between TensorFlow and PyTorch. Anybody has any questions so far about, well, in general, TensorFlow, PyTorch, maybe transfer learning, something like that?
So Tensor 2.0 is quite similar to PyTorch, is it?
Yes.
I mean, it's conceptually similar, right?
Yeah.
Okay.
So this is basically what you should keep in mind. If you're going to use TensorFlow 2.0, then you're good to go. If you're going to use TensorFlow 1.x or 1.8, and there are many companies which actually still use TensorFlow 1, that's very, very bad, right? And of course, if you're going to use 0 point something, you're a horrible person. Anybody has any questions so far? If there are no questions, then we could take like a small break of, let's say, 5 to 7 minutes. What time is it? Yeah, let's come back at around 35 and we will start our lecture. Okay? And then we have the following. Now let's share the screen. Just before we start, I just want you guys to know that the majority of the content, or at least the half part of the lecture, the first half part of the lecture, comes directly from this book. This is one of the best books in machine learning that you would find outside. It's called Interpretable Machine Learning. It's a very simple book, easy to read. It's completely available online, as you can see, and it's definitely like the guide for everything about interpretable machine learning, at least for the starting to work with interpretability and machine learning in general. Very well. So during this lecture, we're going to kind of revise a little bit logistic regression and linear regression again, and revise a little bit on decision trees. And we will speak about what is interpretability, why it's very important, its application areas, the scope or the different levels of interpretability, different manners that you can interpret the model, and of course, the simple models that are highly interpretable, which are, as I said, logistic regression, linear regression, or decision trees and stuff like that. Then we will speak about one method for interpreting all types of data, which is called LIME. And then, of course, we will speak about GradCam, which is kind of the hot new thing for computer vision interpretability. So what is interpretability? Interpretability is the degree to which a human can understand the cause of a decision, right? So let's say we have a, let's change the color. Let's say we have a neural network that is doing cancer detection. Now, of course, we can give it like a scan, and from the scan, it will tell you, yes, this has cancer. No, this does not have cancer. But if it does not justify its decisions, then it's a completely useless neural network, because it does not speed up the work of, let's say, what is it called? A doctor. So a doctor comes in, he would have to look again through the image as a whole and detect where the cancer is on his own. But if it was interpretable, if, for example, it would come at you and tell you that this patient has cancer because I can see the cancer in this area, for example, this would be a very useful model because it allows the doctor to speed up his diagnosis. So definitely, interpretability is very useful in these cases. So right now we will speak about what it is, why is it important, different types of interpretations, and basically these two interpretable models. So this is a picture from, from a paper that we recently published in like IEEE transaction on neural networks and learning systems, which is a very good transaction. And in here we were speaking about some of the problems that the models that we have seen in the last lecture. For example, exactly this one comes from ResNet 50, I think, or 18. I'm not really sure, but definitely from a ResNet model. And it misclassified this horse as an Arabian camel. Why did it misclassify this horse as an Arabian camel? Basically based on this background, right? Because it's in the desert. This is kind of like an Arabian castle stuff. So it said it's most likely going to be an Arabian camel instead of a horse, right? And once we applied some form of, what is it called? Interpretation model, we verified exactly this case. So we can see that the model was very heavily influenced by these parts in making its decision, right? So in order to understand this decision, we needed some sort of interpretability model. So this interpretability model allowed us to understand the weaknesses in our neural network, allowed us to understand the, what is it called? The biases that this model has. So the importance of interpretability, again, is first satisfying the human curiosity, improving recommendations, right? So for example, you have a, like Netflix, and Netflix now is, what's it called? Is trying to propose to you a new model or a new movie. Now, if you were able to, for example, tell it, I didn't like this movie, if the neural network was able to justify why didn't you like that movie, for example, you didn't like it because it was a Russian spy movie, right? A Russian spy movie, and you are a Russian person, you really don't like these, you know, Hollywood movies, which kind of like to depict the Russian person as just either like a Russian spy or a great chess player. So like very stereotypical kind of movies. If the recommendation system was able to understand why behind its, or like the justification behind this, you liked it, you will not like it, that would allow it to basically improve it even further or improve its recommendations even further. Another one is for safety measures, right? So let's say, for example, you are working in or operating in a something related to safety. Well, let's say you're working with some visual recognition system, and the system told you this person, you shouldn't let them in because they are, let's say, a terrorist, or they could be like related to some terrorist organization. And then the model would be able to justify the reasoning. Let's say they have the same nose and same facial features as some sort of other terrorists from before. And the model would be able to basically explain this and say that they look very similar. Another one is to detect biases. As we have seen just right now, we had a case where a very good model, recognized as one of the best models in the world, mistook a simple case of a horse as a camel just because of its surroundings, because the model has this bias within it that everything inside, for example, the Arabian desert should be a Arabian camel, right? So this is like some sort of a bias. Another very, very good example for this one is the fact, for example, that iPhones, their camera now was like had a small problem where basically not a Chinese, an Asian woman just like trained her iPhone to learn her face, and then she just went ahead and showed or tried to unlock her camera or unlock her iPhone using the faces of other Asian people in her office. And basically all of them were able to unlock her phone. This, if we had like some sort of interpretability model on this lock screen or on this security camera for the iPhone, they would have been able to detect these biases against, for example, Asian people or against Black women, for example. Same thing was happening in different banks where they would, or their recommendation system, given like the same features for a Black woman and the same features for a white man, the model would give money to the white man or would allow the loan for a white man, but would not allow it for a Black woman, given the same exact features, right? So basically, let's take other features, income, other features, I don't know, like education level and stuff like that. Given all of these exactly the same, the model would give the loan to a white man over a Black woman. So these are what detecting biases are, and this is a very important part right now. And of course, debugging and auditing the model. So these are some of the importance and application areas of interpretability, and having interpretable models or having an interpretation algorithm, right? So something that takes a black box model and interprets it. There are different levels of interpreting, right? So there is the level that I was just speaking about, where you take one decision and understand why did this happen. But this is just for one decision, right? For, let's say, for example, one patient, understand why does he have cancer? And then there is another level which we spoke about. For example, is the model racist against Asian and Black people or people of color? So this is another level of interpretability. So we're no longer speaking about one instance or about one prediction. Now we're speaking about a group of predictions, right? So there are, again, as we said, several levels of interpretability, and we will go through each one of them right now. So the first level is algorithm transparency. Algorithm transparency means, how does the algorithm create the model? Now, let's say we are building something like linear regression. Linear regression. So we know that the linear regression algorithm trains a linear regressor, which is just a linear function, A, B, C, and for example, B, right? This is x1, x2, multiplied by x2, multiplied by x3. And this is the bias. So we already know that our algorithm will be finding or will be training the values of A, B, and C using a specific formula, right? We have the formula A equals stack something that is calculated from the data, B equals something else, and C equals something else calculated directly from the data. So we already know, or we have a certain amount of transparency for the algorithm. We know how the algorithm trains, or how the algorithm creates the model. Now, the second level of interpretability is called global and holistic model interpretability. In general, it means how does the trained model make its predictions? So what we see is, for example, we take a certain x, which is like a vector like this. What we do is simply send it, multiply it by a, this is x, and then we add b. If it's bigger than 0.5, we classify it as true. If it's smaller, then we classify it as false. So this is a global holistic model interpretability. Do we know how does the trained model make its predictions? Usually for the simple models that we have right now, or what we study, we always have to study like this algorithm transparency and global and holistic model interpretability. So the majority of the models that we are studying, we know these values. But there are some certain cases where we do not know. So for example, there is some model that is being trained by other people, and you're using it as a completely black box. Now, the third level of interpretability, or the third scope of interpretability, is called global model interpretability on a modular level. So the question that you should ask in order to understand this one is, how do parts of the model affect the predictions? So again, let's say, for example, our A, x1 plus B, x2 plus C, x3 plus D. So now the different parts of the model are these: A, B, C, and D. Do we know how do they influence the predictions? Yes, we do, right? So for example, the higher the A, the more influential this feature is. So this is one way of interpreting it. Now let's go for neural networks. And let's say that the weight of this neuron connected to this neuron is very high. What does that mean? Does it mean that this feature is important or this feature is important? We have no idea what does it mean, right? So for example, for the smaller models, such as linear regression, we understand the influence of these values directly. We can interpret it. But for the weights of a neural network, we cannot interpret that one. So this is the third level of interpretability. Now the last two layers, or the last two levels, are very related to each other. Local interpretability for a single prediction. So again, this is for global, no. This is for the model, this is for global model, and this is for the local values. Now the first one is for a single prediction, meaning why did the model make a certain prediction for this instance? Sorry, there is visualizations image that maximizes specific neuron. Oh yes, that's a very good one. So what I'm trying to say is not that neural networks are completely uninterpretable. Let's go back. So I think you are speaking about I forgot the name of these things. Neutron, no. What was the name of that? Logistic regression. Yeah. Let me just 1 second try to find what you just spoke about, because it's pretty good. Ultra, something like that. No, completely forgot. Neural network visualizing weights. No. No. 2 meters. Yeah, this one. Let's check it out. Here it is. So this work does exist, and it allows you to basically understand the weights of the neural network in this kind of visualizations. But me personally, if I look at this visualization, I will know, I will not understand what is this weight doing, right? So probably you would say, oh, it's trying to find the eyes of a cat or something like that. This kernel is trying to find the eyes of a cat or something like that. But I personally cannot interpret it directly, right? Some people say that these visualizations help them to understand if the neural network has biases or not. I certainly have used some combination of these things, but something a bit different than this. So basically you build a 3D space where you are walking and you see the change in the classification of the model. That was pretty useful, but these visualizations didn't really help me understand anything about the neural network. If it works for you guys, then you guys are pretty smart. Trippy, yeah. But that's a very good innovation. Thank you so much. So just to go back to what I've said, so the third level of how do different parts of the model affect the predictions, this level of interpretability. For neural networks, there are certainly some methods that try to interpret the different weights of the neural network, but it still remains pretty difficult or pretty challenging for a human being to understand it looking at it directly. But for other simpler models, such as linear regression, you can clearly say, for example, if A is equal to 5 and B is equal to 0.5, you can clearly say that feature A is more important than feature related to B, right? So this is what this one is. Now, local interpretability for a single prediction, something path to an could lead to for logistical linear dependence of one feature could lead to complications on interpretability. Correct. Certainly, yes, and yes. Yeah, what you just said is correct, Randall. So basically, if you have two features which are highly correlated with each other, that means kind of the interpretation becomes a bit difficult to make, right? And even the training or the model really doesn't give you good results in these cases. So assuming the model is good, assuming the model is well trained and the data is clean, so this is something that you should have taken care of before basically training the model. But if you didn't, it would be bad. But assuming that the model is clean, assuming that the data is well trained, the model is well trained and the data is cleaned, linear and logistic regression are highly interpretable models. Now, let's go back and see the local interpretability for a single prediction part. So why did the model make a certain prediction for a certain instance? So again, we go back to the example of the cancer patient. So for example, this is the human beings 3D scan. And here we can see in his 3D scan, there is some cancer. So let's say our model classified him as cancer, as a cancerous person. If we manage to ask the model, why did you make this decision? And the model pinpoints the location of the cancer, that means it's a interpretable model. If it cannot do that, that means it's not interpretable model. Where is this one also very important? In, for example, bank applications, right? So if you're applying for some loan in a bank, and the bank, for example, tells you, no, I will not accept your loan, then the bank should be kind of responsible to tell you some information on how you can improve your profile to get a loan, right? So for example, you have this income, you have saved this much, you usually spend this much money per month, you never really go down or you never use your credit. So basically you are always using your own money, you never go to minus credit. So all of these features are here. And some of these features are not good for the model. So the model should tell you, I did not accept your application because of this problem or this feature, and because of this feature, try to get this feature above 60, for example, and this feature under 20, and you would get accepted. So this is what local interpretability for one feature. No necessary disk can vulnerability to game the credit system. Yes and no, right? So basically, of course, people could use this interpretation to, make something look more appealing than it already is. But again, some other banks really need this, or some people need this information to thrive. How to make, well, that could be the case. I'm not really a bank expert, but yes, that's certainly one of the cases that could happen. All my banking information comes from Netflix, so I really have no information there. But yeah, this is like a potential example of where you could use interpretability, right? The last part is local interpretability for a group of predictions. And here we are no longer speaking about a certain person applying for banks or for loans in the bank, or a certain cancer patient. Now we're speaking about a group. So let's say if a group of Black women apply, or a group of Black women take this 3D scan and send it through the detector or the cancer detector, are there some hidden biases in there? So for example, is it working as well for what they call for people of color as it is working for white people? So this is very common problem, since the majority of the training data would be data for white people, right? Since the majority of the researchers are white, the majority of the data would also be white people. So people of color would kind of be heavily punished by such models. And this is not just for machine learning, right? So you can find this in medicine also in general. You would see that doctors tend to give pain, what are they called? Pain relievers to white people a lot more than they would for a person of color, because they assume that people of color are a bit stronger, right? And they don't feel pain as a white person does. So these kind of racist, or not racist, but kind of biases that come from things that shouldn't exist, such as the race or the gender or stuff like that, are always there. So we always use these biases in our decisions. And we want to make sure that the neural networks don't fall in the same problems as we human beings fall in, right? So this is what local interpretability for a group of predictions do. And this is a very active area of research. So if you guys are interested in these concepts, definitely it's a good place where you could do your PhD, and definitely something for your master's thesis too. Now that we have spoken about these different levels, let's take an example of logistic regression. And let's go through the different levels of, or different scopes of interpretability that we have seen before. And yeah, try to understand which ones are working and which ones are not there. So the algorithm transparency. How does the algorithm create the model? We have already said that A equals some formula, B equals some formula, C equals some formula, D equals some formula, so on and so forth. So the first level of interpretability is there. The second one is, how does the trained model make its predictions? Again, we know, so we multiply X by the weights and then add the bias. If it's like logistic regression, we send it through sigmoid. If the what is it called? If the probability is bigger than 0.5, that's good. If not, that is bad.
I have a question.
Yeah, go ahead.
Why do we need those two of them when it feels like one of them is equivalent to the other, like transparency and how prediction is being done?
Yes and no, right? So as I said, in the majority of the models that you are learning, that is the case, right? So if you already know how the algorithm is being trained, then you should have an idea on how the algorithm makes predictions. But again, training an algorithm and making a prediction on it, using it, are two different functions. Now, one person would say, how is that? Let's take an example of clustering techniques, right? Let's say we have the you don't know clustering techniques, do you? Randall, you haven't studied clustering, right? So let's say there is this, this is a very advanced case of clustering.
KNN is the one where you pick some random spots and then you keep minimizing distances, right?
Not
No,
really, not really.
in KNN, it's just training is just data and prediction is hard part. You like calculating all the distances.
Ah, yeah, this
So-
is a good example, right? This is a very good example. Thanks a lot, Michael.
So training takes no time. It's just data.
Yeah.
You have it.
So basically, let's imagine this is the data, right? This is class 1. And this is class 2. Now, the model that we are proposing simply takes a new sample. So this is our new sample, looks around its neighborhood and gives it the same class as its neighborhood. So if I put it here, the neighborhood would be, this would be a brown class, right? If the sample was here, this would be a red point, right? So basically the prediction is made based on the distance between these different samples. Now, as your friend said, the training part does not exist. We have nothing to train here. Simply, we save the data as it is. This is the list of the data. We save the predictions, or we save the labels for every single point. We get a new sample. This is the new sample. Compare with each one of them. Find the closest one and take its label. Very simple one, right? Randall, are you here?
Yeah.
Yes.
You pick
So-
representatives, am I correct?
Yeah, so this is one way of, this is the training, right? The training is just saving the data. Now, imagine the model can have, like this is, you know how the training is being done, but you don't know how the prediction is being done. What if I don't take just the closest one? What if I take the closest 5 and take their average? What if I do something completely different, right? So this is what those two levels are saying. So the first level, do you know how the training is being done? The second level, do you know how the prediction is being done? So do you have access to train function? Do you have access to predict function? Yes. I imagine finding closest song.
But isn't this prediction, no, like we're doing something with distance, right?
Yeah.
And we can say the same thing about some loss function, right? We don't know exactly, could be an absolute square or could be one norm or could be infinite norm, something, whatever. So
Exactly.
right, it depends.
Yeah. So our friend Micha also said, what if, how do you define this closest, right? So are you using, for example, are you using Euclidean distance, as you said, so the second norm, or are you using like the infinity norm, or are you using the L1 norm or something else, right? Or Manhattan distance. So definition of the closest differs. And this is what gives you the different levels of interpretability. Now let's go to the third level of interpretability for logistic regression, which is global model interpretability on a modular level. Basically, how do parts of the model affect the predictions? In logistic regression, it's again very simple. So we have, let's say, A, B, and C, and D. The higher A is, the more influential its feature, the lower B is, the less influential its feature is. So this is the third level. The fourth level, how can you make, or how can you understand or interpret the predictions for a single person? Simply, basically what you do, you give him the following. Let's say you are trying to predict the price of a house, yeah? And you want to explain to him, why is this price equal to $500, let's say. So a simple explanation would be to give him the sum right? So you're explaining to him, we took this value, multiplied it by 25, and this value plus something else, right? So you're just giving him, how did you come up with this 500? It could be pretty similar to what we said, how is the prediction being made? So basically level 2 and level 4 are quite related to each other. So level 2 speaks about a hypothetical case, whereas level 4 of interpretability speaks about exactly this case, right? So this is basically the difference. And then the last one is local interpretability for a group of predictions, or why did the model make specific predictions for a group of instances? And in this case, you could try to understand, for example, let's say, Black women. And we have this race feature, right? Race feature, for example, gives you a very high, let's say, what is it called? Weight. So if the race feature has a very high weight, that means the model is quite racist. Now let's go to, for example, if something that is a bit hidden. So if we find that there is a feature, let's call it education, or the university they graduated from. So this looks like it's an innocent feature, but you would find it's highly correlated with race, and it has a high, high weight. That means this is the reason the model is racist. So you understand? So this is one way of doing local interpretability for a group of predictions, right? The next model we're going to work with is decision trees. Decision trees are also a very simple and highly interpretable model. The first two levels, so for example, algorithm transparency, how is the algorithm creating the model? Again, we all know the story. You take the feature which gives you the highest information gain, you split on it, and then at every level you take the highest information gain feature, and then you split on it again, then again, and then again, and then again, and then again. So we know how the algorithm built the model. So this is the first level. I'm sure Randall has no idea what decision trees are, but don't worry, as long as you know logistic regression, the rest should be easy. Global and holistic model interpretability. How does the trained model make its predictions? Simply by using an if statement here. If age is bigger than 25, then you check if income is bigger than 500, then return true. Else, for example, we check how much credit does he have? What is his credit score? If it's high, we say true. If it's low, we say false. And so on and so forth. So this is how we make the predictions. Next one is a global model interpretability, or how do parts of the model affect the predictions? Again, we can easily understand that if, this is the if statement here, if this feature is bigger than a certain threshold, that means this is going this way and this is going this way. So we kind of have an idea, how are these different thresholds, or how are these different features, the level of each feature influencing the predictions. The fourth level is local interpretability for a single prediction. Again, all you need to do is return to him the branch. So let's imagine that this was a tree. So what you need to do to kind of justify is, this was the parcoured tree. So for example, this is the sample. Return to him all of these if conditions, right? So this is an if statement, this is an if statement, this is an if statement. Return to the person these if statements that caused him to go this way. And there you go, you have your local interpretability for a single prediction. And then for a group of predictions, we can do something pretty similar to what we did for logistic regression, and try to understand where is race playing a feature in these in our tree, right? So if race is a feature on its own and we have it at the top, that means it's a very influential feature. If it's like on the lower levels, it's not very influential feature. Yeah, so this is basically what decision trees are, and we have just explained them on the different levels or the different scopes of interpretability. Now there are just like a small set of questions that I like prepared for you guys, just to make sure that you understand very well. So how do you explain a prediction on a certain sample, as we said before? So this is kind of like a small quiz. Did you guys go away or something? No worries, like we will just answer this question and you will get the rest after it.
Could you repeat the question, please?
Simply, how to explain a prediction on a certain sample. So for example, I have a certain client. He was rejected from the loan. How can I explain to him, why did my decision tree reject your loan?
You just give him the path.
Exactly.
Yeah.
You will just give him the path, which is these if statements. Very correct. The second question. So again, as I said, this is just basic questions, just to make sure that everybody's understanding. So the second question, how to change the class of a prediction. Now, if the client wants to say, how can I get the loan, right? Yeah, go ahead.
We provide a shortest path from his position to a different class.
Perfect.
And return like which statement will change the path.
Exactly. So for example, here we had, if income bigger than 500 and our person went down from this side, right? So we gave him false, but if he went from this side, we gave him true. So we simply just return this way and tell him, if your income is above 500, we will accept your, what is it called? Your loan. So this is exactly the correct answer. So we find the shortest path to the class that he wants, and then we give him what are the features that he should change about himself. How to measure the importance of a feature?
The one that are higher and the one that are lower. So
Exactly, right. So for us, the algorithm already starts with splitting on the highest important feature. So we define importance based on this information gain that we get from this feature, right? So the higher it is, or the higher it's always getting, the better. That's very well. Anybody has any questions so far about what we have seen? So what is interpretability? Why is it important? Scope of interpretability, logistic regression, and decision trees. What?
For me, just simple question. Are biases always bad? Because sometimes it's a good feature. Like we don't need to bring politics in our models.
Yes and no, right? One person would say that, yeah, it is a fact that, for example, white people get more, or white people always return the loans that they take are safer, for example, than, let's say, black people. So this could be a fact. So if you just do like, I don't know, some sort of correlation metric between white and returning the loan, black and returning the loan, you might find that there is a higher correlation between these two compared to black and returning the loan. But at the same time, if you look at it from like another perspective, why are black people unable to return the loan? Basically because they didn't get, for example, as good of an education as the white people did. Why didn't they get as good of an education as the white people did? Because somebody rejected their initial loan for education loan, right? So basically they wanted to go to the same university, but they were not accepted. Why didn't they get accepted for that university? Again, you go back to the same cycle of because they are Black, they were not allowed to get a loan of buying a house in a good neighborhood. So they did not get access to good education from like the childhood. So you get into this cycle where, yes, it's fact because it is a fact that there is a correlation between race and returning the loan. But this correlation is happening only because of these models which are causing the correlation to happen, right? So the model is forcing Black people not to have an equal opportunity and then saying that oh yeah, Black people are not returning their loans because they're unable to get the same access to the same features as white people would do. So you see this like loop where you are generating problems and the solution. Okay, got it. So you are saying that is in fact, there is a correlation, but you are the person who are creating the correlation. So this is why racist models are bad. I'm not sure what this is. Whoa, cool. So apparently if you visit canva.live and enter this code, you guys can ask me questions. I didn't know. Oh, this application is pretty cool. Anyway, for now, let's take a small break and come back in 10 minutes or 15 minutes, how much? Yeah, 10 minutes. Oh, no. Yeah, 10 minutes, 10 minutes. We should have stopped 10 minutes earlier and started now. Anyway, let's take like a 10 minutes break. And nice. So far what we have spoken about is what interpretability is, what it isn't, importance of interpretability, the scope of interpretability, and of course, some of the interpretable models such as logistic regression, especially, and of course, what is it called, that other girl? Decision trees. Now for the rest of this lecture, we're going to speak about two algorithms which are very, very widely used for interpretation of neural networks in general, which are LIME and GradCam. Nice. So first we'll speak about LIME. So local surrogate LIME is local, interpretable, model agnostic explanations. So the first part is model agnostic explanations. So we see explanations. So basically we're trying to interpret the model. This method is model agnostic, means it works for logistic regression, works for decision trees, works for what are they called? Neural networks, and works for anything else in between. And of course, local interpretable. Interpretable means it's again an interpretation model method. And the local means that we're going to train in a model, but locally, right? So there is globally on the whole data set, and there is locally basically on a specific part of the data. So we will see it, of course, the algorithm on tabular data, understand it first on tabular data, and then the generalization to text and images is pretty easy. So just to understand what LIME does, so what we're trying to do basically is we're trying to approximate the decision made by some model using a simpler model. So here, for example, we have this sample, and we want to classify this point, we want to understand why did the model make this decision on this point exactly. So you see the original model is pretty complex, right? So it's a very complicated model, hard to understand, hard to interpret. What we do is we estimate or approximate this model locally, very locally, only around this point for using a very simple model such as a linear regression, right? So this is the idea. The idea is to basically estimate or train a new small logistic regression only on this part of the data, which is like close here. Let's continue. So from here, what we do, the steps are pretty simple. We select the instance of interest, right? So let's say this is the point that interests us for classification, and we would like to understand why did the model classify it as a gray point or as, I don't know, something else. The second step would be to perturb, So play around with the data set and get the black box predictions for these new samples. So basically what we do is we randomly generate new data around our target point. So let's say, for example, we have age, gender, something else, and income. What we do is simply put a random value for age, random gender, and a random income, right? And we continue doing this again and again and again and again until we have some population that covers a good amount of the what is it called? The data set space. And then what we do, each one of these new random samples, we send them to our black box model, right? So our model does interpretations or does predictions on these new samples. And then we use these new samples to train the new simpler model, which is the logistic regression. But we don't train the logistic regression directly. We train it using specific weights. What are these weights? So basically, if a point is close to our interest point, its total contribution to the loss function will be high. So remember, the loss function or the error of logistic regression or linear regression, right? It's the MSE between, what is it called? Between the prediction and the real value or the real label. Now, MSE is not mean MSE, but weighted mean MSE, where we're basically trying to attribute a weight for every single difference, so they're not going to be the same. This is a technique that you guys would find or you would study probably in the machine learning course. So Randall, just hang in there and you will understand what these things are. After that, we train a weighted interpretable model on the dataset with the variations. So this dataset is a new dataset. We don't really need the original data, nothing at all. We use this new synthetic dataset. And then we explain the prediction by interpreting the local model. So we build this simple logistic regression. And then if the client wants to understand why was he on this green area, we tell him because you had value bigger than this and you had value smaller than this and stuff like that. And if you want to go to the other class, just try to cross this line. That's it. A very simple model. Now I'm going to have to ask you a small question. How would it look? How would a call to this model look like, right? So let's say I say the following. Interpret. I give it X sample and model. Do I need to give it like the real label of this X? Yes or no?
No, because we trained
Nice.
it with a specific point that we chose, I guess.
Very good, very good. How can I
Sorry?
make a poll? Does anybody know how to make polls in this thing?
Sorry, I don't really get your question. Can you repeat?
Yes. For doing this Lime, does it need as input? So I know that it needs the sample of interest. I know that it needs the model. Does it need the prediction or the correct label for this sample? Just try to vote or just try to say yes or no in the chat. Go ahead, guys. Don't be shy. Just yes or no. Do we need the original label or no? I'm still confused. Okay. I got that. Very well. Let's clean it up. So I've explained to you this logic so far. Can you tell me, in order to run this model or to run this algorithm, what do you need? This is for Sergey. What do you need as input?
We need our sample and our synthetic examples.
Examples, but this is something that you will generate.
We need a model also.
You need the model, or specifically, what do you need in the model? What do we need in the model? Why do we need the model for? What do we need it for?
For predictions?
Yes, we need the predict function only. So we don't really need the model, whatever it is. It's a black box model for us. We just need the prediction function. What else do we need? So these are a must. Is there anything else that is a must? So something that cannot be a default value, something that always must exist there. For example, do we need the training data? X and Y.
Yes,
Who said yes?
I did.
You did. Randall, right?
No, I am there.
Who said?
I did. I am there.
Ayami did. Nice, nice. Can you tell me why do we need the training data to run this algorithm?
Because
Yeah, go ahead, explain.
I'm not sure. I'm not 100% sure.
Just give your opinion. You know, everybody here is here to make mistakes. The more mistakes we make in class, the less mistakes we make in the industry, right?
Okay, so I think like we definitely need like a training data set, because if we don't have a training data set, there's no how to basically know what to predict on or which new points to get.
So you mean that these black points here are the training data set, right?
Yes.
No. So these black points in here are not the training data set. This is the random data set that we have generated. So this is a randomly generated data set by the algorithm.
Okay.
It has nothing to do with the training data set. Very nice. That's good. It's good to make this confusion right now so that it just disappears completely, right?
Can I ask?
Yes.
I just want to clarify all the algorithm. The whole idea of that algorithm is that we have a model and we're trying to, we get a big amount of predictions, After that, we just look at area of interest and
Yeah.
trying to simplify somehow all the prediction and explain it by
Yes,
linear model.
exactly. Yeah. Very simple, very naive idea, but it works very well, right? Now let me ask you a question. Do we need the real label of the sample to run this algorithm? The true label.
We don't need it.
Nice, we don't need it, right?
Prediction will be enough for that.
Exactly, we don't need it, right? We only need what the model says, because we're not interested if the patient has cancer or not. So if we're making this one, we have no idea what the real label is. What we're trying to do is interpret what the model is saying. So we don't need the training data, we don't need the training labels, and we don't need the label for this interest, for this instance of interest. Very nice. So now that we understand how the model works, now let's try to generalize it to different data types, right? For some reason, my brain is starting to freeze, but let's continue. Okay. So now that we understand how to do it for tabular data, let's try to generalize it for text data. Can somebody tell me, why would this be difficult for textual data? What are the problems here? Right. So tabular data looks like this, like a small vector, right? But textual data looks like this. I am a student. What is the problem here? What are the problems that can make this algorithm not work? Or how can we change this algorithm to work on textual data? Go ahead, do not fear like giving wrong predictions or wrong answers. The more wrong answers you give here, yeah, go ahead, Micha. Yeah.
First of all, we need to translate our words into numbers. So we need some kind of language model.
Mm-hmm.
And after that, we can deploy our tabular methods to our data. But how I see the problem, when we're trying to explain our model, it looks only locally, but usually the good features for text data is about global features. For example, is it at the beginning of the sentence? Is it a question? Maybe it is like specific terms or part of the formula. So, so context matters more than local features.
Of course, certainly, it's not going to be perfect, right? What we had here, for example, in this linear, tabular data, we had, for example, age feature, and we managed to understand how does the age feature influence the decision. Now, instead of an age feature, we have words. And we would like to understand how these words influence the decision. So as your friend said, we are going to train logistic regression. That means we cannot use words and we need numbers, right? So how can we convert this into a number?
The easiest way is bag of words.
Okay, go ahead.
So we have a dictionary of all the words that we encountered in the data, and we present our, like, and we put one if this word is in our sample. So we convert our sample in very long vector.
Very long vector. That's a very good idea, but it assumes that we have access to the training data. We don't have access to the training data. This is something that should work for a black box model. something that was trained in India and now it's being used in Nigeria. We have no idea who trained it. We have no idea what it's made of. What is the data that was used for training? We just want to interpret it. So try to use the same idea, but instead of using a very large bag of words, use the smallest amount of words you have access to. What are these words that you have access to?
Sample area.
Yeah,
Oh.
I am a student. And there you go. So this sample is 1, 1, 1, and 1. Can somebody generate another sample? 0, 1, 1, 0. Am a. It's definitely a random sentence that doesn't make any sense, but it is an implementation that works with this algorithm, right? Somebody would generate a different sentence that is 1, 1, 0, 1. I am student. Another one would be like 1, 1, 0, 0. Yeah, 1, 1, 0. I am alone. So these are different samples. This thing could be sent to the model for predictions. So that works. And this thing could be sent for logistic regression for predictions. Of course, this is not an optimal solution because the majority of the sentences we will create will be useless and have no meaning. I am. Makes no sense, right? But for example, if I said I am not a student, I don't really need to understand what is a student and what is am, what is a, what is not. I will just see. Yeah.
In this Lime algorithm,
Yes.
we are selecting a particular data point of interest.
Yes. Yeah.
And then we are doing some data generation to get these black points.
Yes.
Then weighting the sample according to the distance. Proximity.
Yes.
And doing linear regression or something.
Yes.
So what is that predicting? It's just saying like some points are farther away from this point that we generated. Like what is generating these black points? Like is it the original model that we made?
Oh, no, this is just random.
Okay, so what is the aim here? Like why are we like, I don't get what we're doing here. Like we're segregating this.
For example, we're trying to understand, is this about school text or not school?
Yeah.
And we don't know our like model, and we like supply one data point and somehow trying to get the neighborhood of that data point. One of the generation is just drop out the words. I think the better generation is for maybe like go from the translator and back, maybe for translate our sample to Russian and back to English. It's another like data point that is close.
Mm-hmm.
Or maybe use word vectors. That is very useful.
Certainly, yeah. So again, just to answer, I think, the question of Randall, what you were saying is, why do we generate these random points, right? Why not use the original data set and it would like simplify our lives? That's true. Can you open the mic, Randall, and like have a conversation?
Yeah, sure.
Good. So why not use the original data set? The simple question, because we don't have it. We're trying to build an algorithm that works, an algorithm that can be used for inference. Who's going to keep the training data in inference time? Nobody. So if we use an algorithm that requires training data, that's an algorithm that is not going to be used. That's an algorithm to throw in the trash. So an algorithm that should work is an algorithm that doesn't use the training data. But still, we need to have something to train our linear regression on, right? So what we do, very simple, we generate random. You know how to generate random? numpy.random and give it a certain shape. So the shape is 440, for example, by 4 features. Simple. From this, we send them to our model and we get the prediction for this sample. This would allow us to have an idea about how does the neighborhood around here or the decision boundary look like. So
I see.
in reality, we don't see this, this decision boundary like this. The model does not see this, right? This is just for you as visualization. So what we're trying to do with these points is get an estimation of how this boundary looks like. So we put different points here and here and here. If we see that these points are class 1, these points are class 2. So there is certainly some boundary between them. We don't see this boundary in real life, but by sampling in random points and accessing the classes or the predictions that the model is making, we get an idea on where is this decision boundary, and we estimate it using linear regression or logistic regression.
Okay, I see.
Nice. So this is for LIME in general. Now for LIME for text, what we said is we try to represent text as a vector. The good idea would be to represent it. Once you start working with text, you will understand that usually we represent text as a vector, but we use some specific algorithms to do that, right? So there are like word2vec or something like that that does this task for us. But for now, we have no idea what was used for the training. We have no idea what was used for, what is it called? What kind of model is this? We don't know if the model requires word2vec or not. So this is a black box model. We have no idea what's happening on the inside. Only thing we know is it is getting a sentence. What we do is we split this sentence. I am a student. The model, for example, classified this sentence as school-related, as a school-related sentence. Can somebody tell me why is this a school-related sentence?
Because of the last word, student.
Because of the last word, student. So what we are trying to do is find a model or find a method that understands that word student is the reason we classified it as school. So we're trying to find this, this method that gives us the reasoning. Student was the most important feature in deciding it was school related. How do we do that? We put I am a student, send it to the model says it is school related. We put I am, the model says, no, this is not school related. We put the word student alone, for example, randomly. The model says, oh, this is school related. And then we repeat these things multiple times. And we have like a dictionary like this. 1 0 1 1 1 0 1 1 1 1. This is the original sentence. 0 0 0 1 1 0 0 0. And we have the classification, or we have the prediction of the model for each one of them. For example, we noticed that every time the model sees this one activated, it gives you 1. Logistic regression would clearly train a new model. For this one, for example, it would put 500. These others, it would put like 1, 2, and 3, let's say. So after you have finished the training, you can interpret the weights of the logistic regression and understand that the most influential parts of that sentence was the word student. Why are we classifying as school and not as English? No, this is just like this is just an example, right? Yes, yes. Why we only remove words from the sentence? Why we can't replace some words with random words from some dictionary? Yeah, that would assume the existence of a dictionary. That would assume that you know what are the words that are accepted in this model. So we have no other knowledge about the model, right? So we're trying to make this method as black box as possible because we don't know what, yes. So basically we have no idea about anything else about the model, right? So we know that the model is a black box and we know it has a sentence that looks like this. That's it. Anything else that you add on top of it makes the method not a black box method. So whatever what your friend proposed of using, for example, word2vec or something similar to word2vec to convert basically that sentence into like a vector like this one. And then we just randomly generate different vectors and send them to the model. This would work if we assume that our model works with word2vec with specific training. We could say the same with the original example, the one with the points. So why does it work there? Can you explain this, Randall? Can you elaborate maybe more?
Same thing like what Sergey is saying, like Mikhail saying, it impacts the distance, right? So these points in the original example you gave also, these also will impact the distance, right? But they're also
Yes.
random.
Yes.
So why does that work here and not in the
But we are not adding new features, remember. So we're always working in the two-dimensional feature space. Feature 1, feature 2.
Oh, text could be not in two dimension.
Yeah. If you add a new sentence or you add a new word, that means you are working with, for example, you are working with a sample that is with 3 dimensions and another sample of 15 dimensions. You added new words, right? So how can you calculate the distance between this sample and this sample?
Using word2vec.
Yes.
Because I think with word2vec it would work. Like
it would work, but you need to understand what word2vec is, and you need to basically know if the black box model is using
it. Why is it will be not usable? Like we convert our sample to vector.
Yes.
We randomize the vector and convert vector again to the words.
Yeah, this is a method that could exist. You are completely right.
Okay.
Yeah, but this method makes assumptions. So it's less applicable than this method, but it gives better results than the method we are presenting, right? So it's a trade-off. Let's take for example this one for spam detection. Our sentence was, for Christmas songs, visit my channel, and like a wink. Can somebody tell me what's like a dead giveaway here that this is a spam? For example, we can certainly see that the word channel is related to like YouTube channels and stuff, and they always keep on spamming you with new emails or something like that. This wink, certainly something that is not a professional thing to do. So you're not gonna receive a mail from your bank with a wink. So this also could be a good sign that this is a spam. The wink, very nice. So what we do is we represent this as our vector, and then we create random, as you can see, we create random values. There we go. We are creating random sentences. Sorry, let's go back. We are creating random sentences. For example, the first sentence number 2 in here, for song, visit, wink. for song, visit Wink. For the third sentence is Christmas song, visit my Wink. For visit my channel Wink. You see? So this is the data set that we have generated. And already you can see a pattern, right? When this is set to 1, the model is saying it is high probability it's a spam. When this is set to 0, this is small. You see? And then you just calculate the distance between this and the full sentence. And this distance could be anything you want. So basically, visit my bigram is most important. Visit my. You see, this is, here you go. Visit my. They are together here, but they don't give you a probability for. But yeah, that's something for the model to decide, right? So after, let's say, after we ran our line, we created this, we trained our logistic regression, and we got the results back. So these are the feature weights for the logistic regression that we trained. How can we interpret this? Very simple. 6, the word channel or the feature channel has the highest feature weight, meaning it is the word that kind of was a dead giveaway and the word that influenced the model to say this is a spam. This is just an example, guys. Huh? Anybody has any questions about Lime for textual data? Yet? Yeah. Clear for me. Very nice. Now let's go for Lime. Let's go to see Lime for images. Before we speak about Lime for images, let's speak about one very common way of converting an image into an array. How would you convert an image, let's say this image, into a one-dimensional array? Can somebody tell me? We do this operation always, like the simplest operation that you already know.
Flatten operation.
Flattening operation, right? Very well, just reshape, flattening. This is amazing. That's the correct answer. And very simply, right, we could just convert the image into an array like this. And then basically this array goes to logistic regression and the image goes to the model. We do that random changing of the values of the pixels, patati patata, change the correct, do the logistic regression, and then interpret it and understand what are the most influential pixels. But there is one small problem in here. What happens when you have a very large feature space? You get a small problem. It starts with curse. Run convolutions that maximize information gain. Well, that's one way.
Dimensionality.
Curse of dimensionality, right? So the curse of dimensionality is the problem that we would get. So if you take like an image with, I don't know, 1,800 pixels multiplied by 1,800 pixels, that's like a lot of pixels, right? How many pixels? That would be like something around this, right? So it's like 1 million values, somewhere close to that. And logistic regression with millions of features does not really work. So what we wanted to do is basically make it a bit smaller, right? So instead of saying that all of this 1 million feature vector will go to the logistic regression, let's kind of simplify it a little bit. We notice that pixels that are close together kind of have the same values, right? So here, for example, this area if I keep sending all of these pixels together, they kind of are the same value. So the model is going to suffer a lot from like these problems with what are they called? How do we say correlations between the different features, and you're going to have millions of useless features. So they said, let's first group them together, group the similar pixels together, since we have a lot of pixels which are similar to each other, and then make like a simple data set with this part of the image turned on, this part of the image turned off, right? So for example, all of these pixels, we don't take them simply by removing this part from the image and just putting it as blank. How do we do that? There is something called a super pixeling, right? So super pixeling is kind of a clustering technique for images, and it groups the pixels based on their pixel intensities, right? Based on their values, we try to group the pixels together. Okay? So there we go. This is the image now. Now, if we want to convert this into a vector where this is turned on, this is turned off, this is turned on, this is turned off, we would have a feature vector of like 50 maximum, right? So now going from 50, from 1 million to 50, right? This is a very big gain in efficiency, right? So 50, you're not going to face a lot of cursive dimensionality, bag of images, right? Yeah, we keep on doing this bag of words, bag and images idea everywhere. So this is what the original image would look like. And this is what we would send to the model, right? You see, just the same image, but with different parts turned off. We send this image for classification, and we send its feature vector for logistic regression, or for the weighted logistic regression. And then the explanation, what if there is a bird in the sky? Yeah, there's no problem. Like the bird might become, let's come back. So if the existence of the bird in the sky, here, sorry. So yeah, what if there was a bird in the sky here, and we classified this as a bird? Of course, if you remove the bird from the sky, the model is not going to classify it as a bird. If you keep the bird in the sky in the image that you send it, the model would classify it as a bird. After that, you use logistic regression to kind of understand the importance of every single one of these different features, and the model would tell you the feature with the bird was the most important one. Same thing, for example, for cancer, right? We look here. If the model removes the place with the cancer, then the model, if the algorithm of Lime removes the place with the cancer, the model is not going to tell you there is cancer. So the model is going to tell you no cancer. But if the model keeps it, if the algorithm keeps it, the model would say, yes, there is cancer. Logistic regression would pick up on this relationship, and it would tell you the place that influenced the decision of yes, there is a cancer is here. So it would be able to pinpoint the location of the cancer or the location of the bird. Nice. So yeah, this is how the line for images would look like. And the explanation would be highlighting, or like a small image like this, where you have the features that have the highest importance or the highest feature weight, like this. And like that, you would be able to understand whether this feature was important or not. And what you can also do is the opposite. If you can understand which ones have the highest positive value, you can check which one has the lowest negative value. And these are the pixels that are going in the opposite direction of the classification of that class. So for example, if the model, so if you have an image like this of a cat and the dog at the same time, Lime might give you something like these places have a high positive value, and these areas have a low, a very high, like a very low negative value, like minus 60, right? Very low. Did you get it? So basically you can get both. You can get the most influential and the most non-influential, going in the opposite direction. So is it clear so far, Lime? This algorithm. Any questions?
So Lime just can say to us which area is more important for output, but how we can get why exactly that area is important?
That's something that we cannot really like. What do you mean? Why exactly is that area very important, right?
I mean that that algorithm shows which area is important,
Yes.
but why exactly it's important, we can say.
Why exactly it is important? It is important because the model is making its decisions based on that area. Now, if a new person comes in and, for example, looks here, the doctor comes and sees that the model is focusing on this area to make the prediction this is cancer. The doctor would come, look at this place. If he can find cancer here, he tells you the model is doing a good job. If he cannot find the cancer here, he completely ignores the predictions of the model. So we cannot really understand it deeper than that. So this is the most interpretation we can get from this simple technique. Next. Anything more, you would have to use a human being to basically read that interpretation and interpret it using his own brain. Any other questions? If there aren't any questions, then we take a small 5 minutes break and come back to finish GradCamp. Yeah, nice. So can somebody tell me what is the number of channels here?
60.
60, very well. So when you have the number of input channels is equal to 3, that means the dimension of your kernel is going to be, let's say 5 by 5 by 3, right? So basically the 3 input channels would be multiplied by all of this, and they would all give you just 1 channel, right? So the 3 channels would be combined into 1 channel. But then you don't have just 1 kernel, you have 60 kernels, right? So you will apply this technique 60 times. So 1, 1, 1, 1, 1, 1, 1. If you get or you concatenate all of these channels, you would have 60 different channels as the output of your convolution. So after a few CNN layers, right, we get these feature maps. So these are the rectified convolutional feature maps. Simply what they are is just the output, or this is the output of the convolutional layer for the final channel, right? So for the final layer. So it should be like an image like this, but with a very long number of channels, right? Like this. And if we set them apart, they would look 1, 2, 3, 4, 5, 6, 7, for example. So these are the number of values. After we have them, simply we flatten all of this, right? And then send it to these fully connected layers, right? And then make the classification, correct? So this is the basic CNN. So far easy, right? Now what GradCamp does is, once you select for it one value. So for example, I want to understand why is it called a tiger cat? Why would it be predicted as a tiger cat? Simply what GradCam does is it will calculate the derivative of this class with regards to these values. Of course, I'm not going to ask you to do it to calculate derivatives manually, but as you know, the derivatives are being calculated for the training, meaning it's something that is very easy to calculate, right? Something that we always have this, we're used to calculate. Now, for Randall, I'm sure you don't know how do you calculate these derivatives, but surely with Professor Khan, you're going to spend a lot of lectures calculating these derivatives for neural networks. But for the rest of you, this will be simply the derivative of y with regards to each one of these different values. So these are the activations. So it's going to be the derivative of y with regard, the derivative of y hat with regard to an activation A. And this is like the simplest function for derivatives in backpropagation, right? So for each one of these values, you're going to calculate the derivative with regards to this, meaning you're going to have the same size, right? The same size of these filters. You're going to have the same size in derivative form. And when you have it in derivative form, what you will do is you will calculate the mean. Let's call it, you will calculate, So you will calculate the mean of every single one of these, what are they called? These derivatives, right? So we have derivative number 1 or derivative filter number 1, derivative filter number 2, derivative filter number 3, derivative number 4. For each one of these pixels, there is a derivative inside. What we do, we calculate the mean of these values. So the mean for each one of them, and this will be the weight. We multiply each one of them with the mean. So for example, if this window contained a lot of stuff that are influential for this decision of a tiger, that means its activations are going to be very activated, meaning the mean would be high, meaning whatever the values inside this rectified convolutional feature map are, they are the ones that are the highest value. So simply we calculate this weights for each one of them. And then we simply do the summation, right? The weighted average of these feature maps. Because again, if a value of this pixel is highly activated with regards to this class, that means it is very influential for the classification, or like the point that it maps to is very influential, right? And from here, what we simply do is we just combine these feature maps like this, and we send them through a ReLU. This is just to improve the quality of the results. And we just get this beautiful design here. Let's go through it in steps. The first step is to compute the gradient of a certain class with respect to the feature map activations, the final layer of feature map activations of a convolutional layer. So basically, we're going to calculate this one. Now, in here, as you can see, we can take any K, any feature map we would like to add. So for example, we have convolutional 1, convolutional 2, 3, 4, 5, 6, 7, 8, 9. But usually what people like to do is to take the last layer because it contains the most information. But again, the algorithm works however you guys want, right? You can easily calculate the derivative of layer 1 as you can calculate the derivative of layer 15. No problem. After that, you calculate the alphas. The alphas are just the weights of these map or these feature map activations. How do we do that? We just take the average of these gradient windows. Again, the gradient would look like this. So it would be like a, there it is. So it would look like this. And what we do is for each one of these weights or for each one of these gradient channels, right? We take its average, the whole image, we take its average, and then we use that average as the weight to combine the different feature map activations. And then after that, we just apply ReLU to make them a bit smoother, and ta-da, we get the beautiful GradCam. We get this. Now, a very good question here would be, the size of this image is not the same as the size of these rectified convolutional feature maps, right? So because the input of convolution is always bigger, or at least always bigger or the same size of its output, right? So this is the output of a convolutional operation. This can be solved simply by upsampling this feature map to the same size of the original image, right? There we go. This is what our heat map would look like for the dog previously. And then we just upsample it to look something like this. And that's it. This is the method. It's pretty simple method, as you guys can see. Anybody has any questions about GradCam?
Yeah, I have one. So we can run GradCal algorithm only during training. Yes.
No, but we have the CNN, right? You can calculate the gradients whenever you want.
Okay.
Yeah.
Okay, got it.
So I'm saying it's very similar to the training part, right? So the calculation of the gradient is the same thing we would do in the training, but you don't need to do it only in the training, right? You can do it anytime you want, as long as you have the output and you have the CNN weights. So this is not a black box model, right? Right now we can access the values of the CNN. I think we could finish this lecture right now. And if you guys have any more questions, what I will do is next week, I will start with a small revision of this lecture. And then we get like you ask questions and then we make the quiz. Okay. Okay. Thank you guys so much for attending. If you have any more questions, please send them to me on Telegram, and see you next week, and prepare very well for your quiz. See you.
Thank you. Bye-bye.
Thank you.
I have one question.
Yeah, go ahead.
Actually, it's regarding those mini projects and that main project. Like, can you please elaborate what do we have to do on those? Should we start somewhere? Or?
For now, there is nothing you should do. Just next week, we will explain them a bit more.
Okay. Thank you.
Nice. You're welcome.
I'm probably like skipped the previous lecture.
Yes.
Is there any kind of assignment that I skipped, because I don't see anything in Moodle?
So far, we don't have any assignments. We have like 3 homeworks, and they're very basic, very simple. I will give you the homeworks once we get there.
Oh, okay.
Yeah, for now, everything is pretty simple.
Yeah, thanks. Because I was afraid that I like skipped something very important.
No worries. No worries.
Okay.